Good morning, folks. We are ready to get going this morning. And a couple of reminders on the board here where we've got PLC 6, which is the review. So I've got a couple of questions out there for you just to get the mental highways open. Homework 3 and Celebration 1. I'm going to go ahead and push those off till Thursday of next week. So we get one extra day. All right. So we'll do those on Thursday. The celebration, like I said last time, will be open all day, and you can pick your time, sit down, do it, and crank it out. All right. With that being said, the topics will include both the ray optics that we have started with, plus the wave optics that we have been discussing since then. And that means mirrors, lenses, combinations of lenses and mirrors. And then we moved into interference, and interference of two slits, interference in thin films, and now we've moved into single slit, and that's called the diffraction. We're going to talk about a little bit more diffraction stuff today, and possibly a little bit more tomorrow, which is why I thought it'd be nice to get the 1 week separation between stopping this material and having a celebration on it. All right, so last time I think I pretty much finished up the single slit description that we're going to go with, and what I wanted to do today is begin on what's known as the diffraction grating. So in order to do that, what I want to do is think about the two slit experiment again, but now we're going to start letting the number of slits get larger. So instead of two slits, let's go to three slits. All right, and let's take a look and see what happens when we think about the interference or diffraction, if you like, in multiple slits. So let's take a look and see. If I take our standard two slit setup and instead I just make it a three slit setup, like this, then I've got our standard slit width, say, perhaps being A, like so. And the separation between the slits would be D. So I could say from this one to this one, and I'll just do a couple of these that are representative, and they would be true for all of them, in which the slits are all separated by D, and all the slits have the same slit width of A. All right. Now, if we consider a screen out here, and we're going to think about the light that comes out of the slits, because we are illuminating the slits with our laser source. Okay, so straight across means the same thing as what's been happening before. We should have a bright central maximum. Okay, but now as we start going off to the side, we want to start thinking about what is it we're going to see. So let's take a look at a couple of trials to try and see what type of pattern is going to ensue from this. All right, so we're going to go like this. Suppose I'm just going to I'm going to pick an angle like that, and I'm going to say, all right, let's suppose that we take a look at this. Now, let's imagine, for example, that the path length difference between each slit, which I could find by dropping a normal from this one like that, and then dropping a normal from this one like so, those path length difference should be the same, because the D, which is to say the slit separation, is constant between the two, right? It's a consistent slit separation. And we're assuming that they're all going at the same angle. So the path length difference that we calculated from the double slit, which was D times sine theta, that would be true for both of these path length differences here. So they should be the same. Let's go ahead and start by looking at the easy case where there's one wavelength in the path length difference. All right, well, if there's one wavelength in the path length difference, then this one travels some number of wavelengths. This one travels one more wavelength, and then this one travels two more wavelengths than the first one. okay? That means they all hit the screen in phase and they come to a bright spot, all right? So happy days. And you could imagine doing a steeper angle, same idea, path length difference now instead of one wavelength is now two wavelengths. So I'm gonna go I'm gonna go some wavelength here, two more wavelengths, four more wavelengths, and I'm gonna get another bright spot, all right? Because they're all gonna be swimming in phase. Okay, if, however, we consider something like the outer two slits having a path length difference of one wavelength between them. Okay, so in other words, now I'm going to take this normal here and I'm going to extend it down here. Right, so now I can see the path length difference of the lower wave with respect to the top wave. And now suppose I've got one wavelength in that path length difference here. So if I have one wavelength in the bottom, if I have one wavelength difference between the two outer waves, that must mean I have a half a wavelength difference between the top and the middle. Okay, so that means I'm going to get some pairwise cancellation here, right? I'm going to get these canceling out, but I'm going to get this one left over. And for right now, I'm just assuming one wave coming through. So we've narrowed the slits way down again. I'm just assuming we've got one wave coming through, right? That means these two can cancel each other, or if you like, these two, but I'm left over with one, right? So there's going to be some situation here where I'm going to get bright spots like I normally do, but then I'm also going to get like a partially bright spot. And this isn't a part of another maximum, where typically you think of the brightness of the maximums as being very bright, which is where we talk about the complete constructive interference, and then it drops off to either side. This is a situation where we have a completely different angle and a slightly bright spot, which is not as bright as the other ones. So there's going to be some intermediate maximum formed between two of the, I don't know if you would say the usual maxima that we would expect from interference in a two slit or a multiple slit situation. All right. So if I think about the path length difference, equaling, for example, one wavelength, then what we find is complete construction. And it should be a very bright spot. Right? Because if the path length difference is one wavelength, then it's one wavelength from here to here, one wavelength from here to here, and everybody's doing the same thing. That means everyone's constructing. But if I then instead find path length difference now between the outermost ones being one wavelength, which means between each successive one, it's a half. PLD is now a half wavelength. I'm not going to find complete destruction. Right? I'm not going to find complete destruction, because you can imagine that if I widen the slits out and I think about more than one wave coming through each one, well, then I'm going to think about most of the waves in here coming through and constructing, right? But most of those ones could cancel with most of these ones, and that would leave most of those. Okay, so we're going to get partial construction, which means it's going to be a partially bright spot. Okay, and and what that means is that we have still the same situations of bright and dark spots, but instead of being bright, dark, bright, dark, bright, dark, what we're going to notice is it goes bright for the central maximum. It's going to go dark while they're all out of phase. It's then going to go partially bright and then dark, and then fully bright and then dark. And it's going to repeat this partial bright, dark, full bright, dark, partial bright, dark, full bright, dark. So let's see if we can take a look at this. I've got got this set up for us here. So if we take a look at this, and if I can set it up so that you can see it, which is certainly highly doubtful, go like this. Now, what do I have here? So let's turn this on. Okay. All right, yeah, you can see that. Now, it's tougher for you to see that. From what I'm looking at, you can certainly see the diffraction pattern from the single slit. In other words, these darks here followed by a bright followed by a dark. That's not the interference pattern. That's actually the diffraction pattern. That's the single slit pattern. And unfortunately in here, it looks like it's washing out all of the interference brights and darks that you're going to see. So I'm wondering, no, you can't see it if it's on. I'm wondering if I had something with a little bit less intensity to it. If I shine it on my dark shirt here, maybe you'd be able to see it. And it looks like probably not. So anyways, we have that happening. Let me do go to 3, like so. Okay. So if we go to 3 slits, and what we can see, let's try if we go, I'm kind of interested now, if we go back here, make this pattern a lot larger. Like that. Maybe it'll be a little bit less intense. Let's see here. Yeah, you can kind of see it, I think. You can kind of see it. So, you see there's an extra spacing between these. There are very bright ones, and then there are kind of dimmer ones right in the middle of those. Okay, curious. Now, I wonder if I can turn the lights up and see that. I actually think this is not going to help. I think this is not going to help, but I was wrong because it looks like now maybe you can see them a little bit better. All right, so this is totally washed out, and it's very difficult to see that. But if you look out over to the side, I'm going to go over here. If you look out over to the side, maybe you can convince yourself that, let's see here. If I have, where's my pen? If I have a bright spot right here, I have a bright spot right there, and I have an adjacent large bright spot right there, slightly off. Right in between those two is a partial maximum. All right, so I kind of like this. So let me try to even a little bit more. Let me try to even a little bit more drastic here. Let's do this. I want to do this like that. All right, so let's see. I'm going to go like that. Let's put it right there. All right. My goal is not to walk right into the laser beam with my eyes. All right, how's it looking now? Yeah, I think you can see them. I think you can just barely, maybe you can just barely make out between the 2 bright spots. There's a small dim one right in there. Well, hopefully you can. If you can, great. If you can't, what can I say? I tried. Oh, maybe the dark shirt works really a lot better now, doesn't it? Oh, there you go. Look at that. Oh, if I stand right here. Okay, so now what do we have here? We got bright spot, and then another really bright spot, and in between them, partial. That's what we're talking about. That's what's left when you get some cancellation between some of the waves. So this is a 3-slit pattern. And we notice that one other thing is happening, which is that the bright spots themselves, these very large bright spots, let's see if I can get this one right here, is actually smaller than it was in the 2-slit. Okay? So, this is going to be a fun game. So let's go to, that's the 3-slit setup. So let's predict, what do you think is going to happen in the 4-slit setup? Okay? And now let's see if we can reason this out. If I think about the 4-slit setup, then, and take all this away, then I'm going to still think about partial construction. I'm just going to make myself another slit right there. Okay, so I'm still going to think about full construction, I should say, like that. There comes another one from the bottom, like that. So here comes that one. Now I'm going to still think about full constructive interference, which should still happen. Now if I go this one like that, and I go this one like this, now if I think about the path length difference between each one, and I say, again, the path length difference between each one could be one full wavelength. In that case, this one constructs with this one, constructs with this one, constructs with this one. They're all swimming together, should be a definite bright spot. What if, however, I take one here in which I say that the path length difference from the first one to the third one is one full wavelength? Is that going to work? No, I don't want to do that. What if I do, I guess I'll do the same thing as I did before, because now I'm kind of dividing it up into thirds, which is a little bit harder to intuit, but okay, let's see. So if I make the full one, if I make a full path length difference, if I make the path length difference a full wavelength, actually I do want to try this. If I make this a full path length difference, this one full wavelength between 1 and 3, so then 1 and 3 construct. That would mean 2 and 4 should also construct because they're the same distance away. All right, so that's not going to work. But that means I'm going to get a bright spot at that angle as well. Now let's go to outer ones being one full wavelength apart from each other, which means that here I have one full wavelength in the path length difference between the top and bottom slits. That means I'm going to have one full wavelength between here and here. That means I'm going to have 2/3 of a wavelength between this one, 1/3 of a wavelength between these ones. And if you think about what's going on with these, I'm going to get 1/3 of a wavelength different from the top one, 2/3 of a wavelength different from the top one, but that means these two are different by a half a wavelength. So that means these two are going to cancel each other, right? Because 2/3 is, or 1/3 is half of 2/3. So the second one and the third one are out of phase by a half a wavelength, and that means I have a constructive opportunity here between 1 and 4. Okay, so I've got that going on. I also am going to have another situation where if I did have this one being if I did have this one being a half a wavelength off, then that means this one's going to be 2/3 of that, or 1/3 of that off of that. So that's going to be a 1/3 of the wavelength here, and that's going to be 1/6 of the wavelength there. And it's not so easy to see how that one's going to construct. But there's going to be a couple of different situations. I'm going to again get going to get situations where I have all of them being constructively interfering. I have some of them constructively interfering. Okay, so let me go change the pattern here to 4 slits, and that way we can see that you'll find, let's see here, that's 3 slits. So just for comparison, here is the 4-slit pattern. Okay, so now I'll stand in front of it so maybe you can see it. Yeah, there you go. So now you can see bright fringes. This is where full construction is happening, and now I've got 2 in the middle where there's some partial construction happening, and I've got another bright fringe here, and then two more in the middle. So you're going to see that as I increase the number of slits, what's happening, and also notice that the bright fringes themselves are narrowing, okay? So what we're seeing here is the pattern of when I increase the number of slits, then I'm noticing that the bright fringes are getting more distinct. They're getting more defined in their locations, right? They're getting narrower, and instead of being really large, they're now smaller. And these intermediate maxima are dimmer, are reasonably well dimmer than the total bright ones. I shouldn't be pointing at that, I should be pointing at my, right? These ones here are very bright, but these in the intermediate are much less bright, okay? So what do you think is going to happen if I switch to a 5-slit pattern? How many intermediate maxima am I going to see? Let's go do that now. We'll switch this to the 5-slit pattern, like so. And we're going to now look at, okay, when I see the situation of them all swimming in phase, yeah. Okay, let's see if I can stand in front of it here so you can kind of see. This one's a little tougher to see, but I've got definite very bright ones here where they're all together. And then I've got two on either side of that. Okay, I've got the two, wait, like that. I got two on either side of it, right? Those two are partial maxima, but then there's one right in between, and you probably can't see that really well, but it's right in between those two partials. There's a much dimmer one right in there. So now I have three partial constructive fringes with the full constructive fringes. I've got three partials in between every full, and again, the full fringes have narrowed, and we're also seeing that those partial interferences are less bright, continually less bright. So just for comparison, I'm going to switch back to the 2-slit pattern so you can get a look at what the fringes look like in the 2-slit pattern. And then you can compare those to this one. So let's switch back to 2. All right, here we go. 4, 3, 2. Oops, that's the one right there. Okay, so now, let's see here. So now if I stand here, all right, there we go. Now if I stand here, now look at what these are. These are all the full same, or at least they should all be fully the same brightness. Obviously the diffraction pattern is causing diffraction minima out here, right? Like this and like this. And at least in here, you're seeing, yeah, for sure, these are all pretty bright. And look at how sizable they are. They're much larger than those ones that we were talking about with, say, 3, 4, or 5 slits, where they had gotten progressively more narrow. Okay. So we find a particular condition where the waves are able to fully construct in certain spots, but it gets more difficult, right? Because it gets more difficult. As I go to more and more slits, then the angle at which I find all of them to construct gets very precise, because I have to have a full wavelength in the path length difference between each slit. And that's where they all line up and swim constructively. Okay, so if there's one wavelength in the path length difference, then that's a very specific angle. And if I'm off from that angle and I'm increasing the number of slits, I'm starting to find that some of these are going to be canceling with each other. Okay. Okay, so let's go back and see if I can get this to come here again. All right, turn that back on. All right. Turn that off for now. And want to take a good look at what happens with many slits. All right, so the pattern was, we noticed that the fringe size, like you would say the Y value of the fringe size decreased. In other words, if I drew the interference pattern, it used to be something like this, right, where the fringes, so on the screen, what I'm looking at is a fringe which is very bright right there, dark here and here, but the fringe spacing, right, this is that's the entire bright fringe right there. Now as I go to 3 slits, that would be for the two slit pattern. Now as I go to the 3 slit pattern, when I go to 3, let's go to 3, what I'm going to notice is they go, here's my central right here. So my central looks like this, and then I'm going to get one like this, and then I get one like this, like that. Okay, I'm getting a pattern that looks a little bit like this, where I'm getting these partial maxima, right? And the sizing of these is starting to decrease. The sizes of these very bright fringes is starting to decrease, and the sizes of these intermediate fringes is also small to start with, but they are dim, or they are dimmer than the very bright ones. And so that pattern continues. As I increase the number of slits, I find that the spacing between the bright fringes becomes very well defined, right? It doesn't kind of like leak off like this, where I've got all this space here to say I've got kind of a bright fringe here and a bright fringe here. It gets to be very narrow, right? These peaks eventually start becoming quite narrow. And then between them, since as we went on to 4 and 5 slits, we found that the brightnesses of these things decreased. We find as we go to many slits that these things disappear altogether. Because when I go to many slits, then what you're talking about is keeping track of what happens when these are not fully in one wavelength difference, right? What happens when they are not fully constructing? Well, when I have so many slits and they are not fully constructing, then they're mostly destructing, right? They're mostly destroying each other. So that I come to a pattern where there's a central bright fringe, right? As usual, anything light can always pass straight through, but then there's a lot of darkness, and then there's another fringe way over there, all right? And so we call this the grating. When we go to many slits, and I'm talking like thousands and thousands of slits per centimeter, okay, where we were talking about possibly having, maybe having what we had like 0.5 millimeters between each one, so that's 20 slits. That's a spacing of 20 slits per centimeter. I'm talking about maybe tens of thousands of slits per centimeter, right? Where you've narrowed the D so much that you have so many slits that it's almost completely impossible to get them all to construct. And when they do, there's one spot where they do. Okay, and this is known as a grating. When we're talking about thousands and possibly tens of thousands of slits per centimeter, this is known as a diffraction grating, because it's like a water drain. When you're walking around, you look at the curb, right, and you see the where the water drains in. It looks like it's a grating, right? And that's what a grating looks like. It's just this, but these are really narrow, and there's lots and lots of slits in a tiny distance. Okay. So let me show you a little bit more of that. There are a lot of really fun patterns that can emerge when you look at this. Let's see. All right, I'm going to show, I didn't bring in a standard grading, so let me go find a standard grading here for a second, and I will show you that. All right, I've moved the laser in a little bit closer, and this is what a diffraction grading looks like. I'll try to stand to the side here, and you can see that there's, let's see if I put it over some of my writing, you can see that there's a little bit of difference in the intensity of the writing as you look at it. All right, so there's definitely something going on, but this is essentially transparent. If you look through it, you can see light through it. But there are so many slits. In fact, this one is, this is an old style. This is 15,000 slits per inch. So if I hold this over the laser, you can see the bright laser right here. And if I hold this over the laser like so, then what you notice is it divides it up, right? So the central maximum is still the central maximum. But what's happening now is I'm getting bright maxima, very well defined, right? And nothing in between. There's no light that's visible between here and here. Yes, light's hitting there, but it's all hitting destructively because there's very little chance that you're going to find a spot where they all interfere constructively. In fact, there's only a few of those spots, right? There's only a couple of spots where that's going to happen. So the diffraction grading effectively splits up and the wavelengths, right? So if I shine a particular wavelength through here, I get very well-defined spots. If I shine white light through here, then I get a rainbow, because what it does is it'll say, oh, if you are this wavelength, then all of the interference happens over there. And if you're this wavelength, all the interference happens here. But if you're this wavelength, it's going to happen over there, right? So what's happening is that a diffraction grating acts a little bit like a prism, right, where it splits up the wavelengths. And also it gives you the ability to measure the angle very precisely, and therefore you can calculate the wavelength very precisely, all right, much more so than in a prism. Okay, so with a diffraction grating, we get very well-defined maxima. And not much in between those. And so where are the maxima? Okay, so we're gonna try to use a locator, just like we had with the double slit interference. And that was basically what I talked about before, where I have one wavelength in the path length difference between adjacent slits. As soon as I have that, then they all constructively interfere. That is the condition for constructive interference in the diffraction grating. Okay, now they are going to be located at the same. You can calculate their locations in the same way that you can the double slit, right? Because it'll still be pairwise cancellation, or should I say pairwise construction is what I should say, right? So that's the same as in the double slit. That's not an accident, okay? That's acknowledging that the only time you're getting constructive interference is the situation where you forced it, right? You have to have constructive interference because there's one wavelength in every single path length difference. So all you have to do is find what angle that occurs at. Okay. Now you noticed that the angle of the first maximum in a diffraction grating will seem to be quite large. Let's see if I can just show you this here. Okay, so here's the central maximum. Now, here's the diffraction grating. I'd like to be able to just hold it right there with something, but I don't think that I can. Okay, how about that? Okay, we can hold it right there. All right, so here's the central maximums, this one. Okay, and we've got first, it's kind of tilted, sorry about that, but that's all right. So I got my first maximum here. This is the m equals 1, and here's the other m equals 1. I don't know if you can see the 2. Yeah, you can. This is the 2 way over here. This is m equals 2. All right, so there's really no point talking about the interference minima because there's a lot of them, right? That's an entire minimum right there. So we locate the maxima with the same exact condition that we use in the double slit, with the caveat that I want to now compare this with the double slit, with the actual double slit itself. Okay, so if I take the grating off and I put the double slit back up, which is this. Oops. Let's see if I can find it here. Okay. So there's the central maximum still here, but where's the first maximum? Well, you can't even see it. It's so close. You can't even see it. Okay. So the caveat here is that in the double slit experiment, we were free, because of the small angles, to replace this with a tangent in which we could use the screen spacing and the distance between here and here on the screen, right? We'll call it the y value. But notice that in the diffraction grating case, that's not a possibility, because the first maximum doesn't occur until well over here, whereas I can't even really show you here. The first maximum is right there, and then the central maximum is right there, and then the first maxima on either side is like that. Okay, so I'll turn this off so you can see. My 3 tiny little lines right there, that's the central maximum, and that's the first maximum on either side. That's a small angle, right? I'm talking about, this is about a 1 meter screen distance here. So these distances are really small compared to 1 meter, but these aren't. So in a diffraction grating, no small angles. You have to calculate this angle. Okay, this must get calculated if you want to use the locator here. All right, you have to calculate what that angle is. That still means that you use the tangent and you use the y over d, but now you actually have to do the inverse tangent and then do the sine in order to find what the angle, and then take the sine of it. Okay. All right, so this must get calculated. All right, and then find theta from the y over d of the tangent, and then use that angle in here. All right, so that's one thing to notice about this. A couple of other things to notice about this. The fringe number on our screen here, I could see the 2. I don't even think I could see the 3. Let me take a quick look. You won't be able to see it because it'll be well off the screen. Okay, so let me see if I can just hold this here. Do I see a 3? Oh yeah, it's way over there. Really dim, but that's it. I don't see anything else. I'm just kind of moving them around so I can see it. I see it on this side. There's the 2. I'm blocking the 1 here. I'm blocking the 1. The 2 is a little bit further away, which you can't see on this side. And then the 3 on that side I can't see. But the 3 over there I can see. And I would estimate that it was probably at least a good 2.5 meters to the side. So in most diffraction gratings, that fringe number is not like it was for the double slit, where we might be able to get in 10 fringes or 11 fringes or something like that. You'll be lucky to get 3 in the diffraction grating. So typically this is a small number, usually less than 5 on a side. I certainly don't see them. They do get pretty dim pretty quickly, usually less than 5. Okay. Now, that's one thing. One other thing is, what are we using for this little d? It's still the slit spacing. Okay? This little d is still the slit spacing. But we have to now calculate this. The slit separation is not given in diffraction gratings. Okay? So when you don't have these, you folks don't come to my live lab. So you don't have these things where they tell you really nicely what the slit spacing is. Here it's 0.25 millimeters, right? You had to use the comb and you had to kind of line up the ruler to it and then count how many there were and try to figure out what the little d was, right? Okay, but there was a well-known slit separation, and that procedure that you used in determining the slit separation between the comb fingers is basically the same thing we use in the diffraction gratings. In other words, they don't tell you what the slit separation is, you actually have to figure it out. I mentioned here in this one that these are 15,000 lines. It says lines, which means slits, 15,000 per inch. So that's not the same as a centimeter. So let's say there's like 40,000 per centimeter, okay? That's the number you're going to get from a diffraction grating, and that's the number you need to convert into this little d. Okay, so let's suppose that we have a number like 40,000 slits per centimeter. And by the way, you in this case, I don't really know why, but you will often see lines substituted for the word slits. You'll see 15,000 lines per centimeter, or like it says in this one, it says lines per inch, or lines per centimeter, right? So that is a piece of language I'm just going to let you know about. Okay, so from that, we need to calculate what the d is. And it's pretty much not that, it's not, it is as easy as you think it is. You just flip that over, right? And then you go, oh, I've got 1 centimeter with 40,000 slits, so it's each slit separated by 1/40,000th of a centimeter. But I'm just letting you know, that's a situation that you're going to have to deal with. So in using the diffraction grating locator equation here, if you like, the fringe locator, it looks like the double slit, but you can't use it exactly in the same way as we use the double slit one. There are a few things that need to go along with it, right? Most notably, finding of the little d, and also not using the small angles. All right, those are kind of the biggest things to deal with here. All right, so let's do a couple of examples here with this. Actually, what would be pretty cool, since I have already marked these out on the board, is to go ahead and use my data to try and find what the wavelength of this light is. So let's do this. I'm going to use, that's at 55. So 55. All right, so the distance from slit to screen is 1.33 meters. Let's do this. Let's find the wavelength of the laser I was just using here. All right, I've got a screen distance of 1.33 meters. I have my distance to my first bright fringe on either side. So what I'm going to do is I'm going to measure between those and then divide by 2. Or if you like, you could take a measurement here, and then average the 2, just to make sure that they're copacetic. So from here to here, it's looking like 91 centimeters. Okay. So I'm measuring the y distance. So this is really y. So y to 1 would be 91 divided by 2 centimeters. That will give me this. It's 15,000 lines per inch. Criminies. I can't question mark. I'm going to have to find that from 15,000 lines per inch. Why didn't I bring out one of the ones that had centimeters on it? Okay, so if we do that, that's, let me just grab this. So this is 15,000 divided by 2.54 centimeters. So that's 5,905. 5,900. I'm just going to say it's 5,900 lines per centimeter. So I would need to invert that number to find my little d. And so that looks like 1, 2, 3, 4. That's 1.7 times 10 to the minus 4 centimeters. Okay, like so. Now, sometimes that's useful. Sometimes it's sometimes you can take a shortcut to it. Okay, so that's kind of cool too. Let's take a look here. Okay. So if I do this, I'm going to solve for my lambda, and that's going to be d, well, it's just going to be equal to d sine theta, right? D sine theta. Okay, so I need to calculate theta, in which the tangent was equal to 91 over 2 centimeters, and that's going to be divided by 133 centimeters. Okay, like so, and then that's going to give me an angle. All right, now do take care with your angle measures in this case. So we're going to do, we're going to clear that off. We're going to go 91 divided by 133. So that's 0.34. Now I'm going to put my calculator into radians, and I'm going to take the, so that's the tangent. I need the inverse tangent of that. Of that number. So that's 0.33 radians. So 0.33 radians. Still small. 91 over 2 divided by 133. All right, so now let's take the sine of that angle. Yeah, it is, it's 0.3. So my baloney about the small angles is not great news right now, but nonetheless, you will definitely incur a problem if you use it consistently, whereas you won't if you won't. All right, we're going to take that, we're going to multiply by little d, which is 1.7. All right, so I've got 1, 2, 3, 4, 5. I've got lambda turning out to be 5.5 times 10 to the minus 5 centimeters. Is that right? Because I used centimeters in my little d. Which hopefully translates to 550 nanometers, unless I counted my zeros wrong. I see a nice 550 right there. 1, 2, 3, 4, 5, 6, 7. Yeah, 550 times 10 to the minus 7 is 550 times 10 to the minus 9. So yeah, 550 nanometers. So it's a nice bright green, and that's what we got. Alrighty. Okay, so just a little bit of fooling around with some of that stuff. Let's do another example here. We got, how much time we got left here? A little bit of time left. All right, let's suppose we do another example of, let's get rid of this. Put this away so I don't smash myself. All right, let's do another example here where we have another diffraction grating. Now we have two wavelengths getting shined through, and we're going to look at some angular separation and things like that. So let's do this one, where in this case we know that the grating has 180 lines per millimeter. Okay, and we have only two wavelengths, and when we shine them through, they're going to get separated, right? They'll be coincident at the central maximum, but they will be angularly separated when we start looking at the first and second maximum. All right, so we're going to shine through lambda 1 of 400 nanometers and lambda 2 of 500 nanometers. Okay, now what I want to know is what is the angular separation if I look at the second maximum. Right? If I have the central maximum, there's no angular separation. By the first one, there'll be some. By the second one, there should be two. Okay, so let's take a look. And let's find by what angle are they separated? Are the lambdas separate in the m equals 2 bright fringe? All right, so what this looks like is there'd be a central bright fringe here where they would be overlapping. And then here you'd have one, and here you'd have another one, and this would be the m equals 1. And then out here you'd have one here, and you'd have m equal to 2, like this. So it's that the first order bright fringe is there, the second order bright fringe is here. All right, and the question is, what's basically the angular separation between these two bright fringes here? All right, so let's just go through and kind of, I mean, there's a couple different ways you could do this, but let's brute force it the first way. And let's just solve for what these angles are. So we know that the sine theta is going to be m lambda divided by d. And the d we know is this, or it's related to this, right? And we're looking at the m equals 2 stage here. So let's look at sine of theta 1 as being 2 times lambda 1 divided by d. And we'll look at sine of theta 2 being the exact same thing, 2 lambda 2 divided by d. And if we solve for these angles, we can then just subtract them. So here we're going to do 2 times 400 nanometers. And if I do that, I got to be careful with my millimeters in the little d here. So I have a couple of choices. I could certainly just take and figure out what little d is. So I could take and figure out what little d is from this. Little d is 1 divided by 180. It's 1 millimeter divided by 180. That would put it into a fraction of millimeters, and I could convert that into nanometers because there's 10 to the 6th in there. Okay. So what I'd want to be careful with here is when I divide by the d, I'm basically going to divide by 180, but that's going to be millimeters. So let's suppose that it's 180, 10 to the 6th nanometers divided by 180. That's 1,000,000 nanometers, because nano is 9 and milli is 3. So yeah, that's right. So I should be able to flip that over and multiply by that, right? So I should be able to multiply by 180 and divide by 10 to the 6th. Seems like that's okay. I do the same thing over here with the other angle. I do 500 nanometers. I'd multiply by the 180 and divide by 10 to the 6th. That'll give me the sines, and from that I'll be able to back calculate and figure out what the angles are. Okay, so let's see, I did calculate these angles. I got 8.3 and 10.4. So for this one I got 8.3, and for this one I got 10.4. And that means that the difference in angle between the two is about 2 degrees. And that's between the two dots given by the second interference maximum. All right. One question you might have is, well, how many total fringes are present for each one of these things? Okay. We are here in the m equals 2. Okay, how many more are there past that? Okay, what's the total number of, let's find the total number of fringes for each one. For each wavelength. So this procedure basically follows exactly how we would have done it in the double slit experiment, which is to say that when you look at the setup for it, okay, the setup usually is something like this. Here's the diffraction grating, like that. Light is shining through this way, gets through the diffraction grating and is going out in all directions like this, but it can't go more than 90 degrees, right? The screen is over here, but it's not going to go backwards. Well, okay, it can go backwards because it reflects, but that's not what we're talking about here. It's diffracting. We're talking about it going into the slits and then interfering from there, but like in the forward direction, okay? So in order to find the total number of fringes, we would just maximize the angle, right? Say that the sine is equal to 1, and try and solve for the m value, right? So what this would mean is d sine theta divided by lambda should give us the maximum m value if I set this thing equal to 1. In other words, d over lambda. So if I have two wavelengths, I'm going to find a one for the 400 and one for the 500. D is what is the same thing as what we had before. So for 400 nanometers, we could use m maximum equaling 180. No, sorry, 10 to the 6th. 10 to the 6th divided by 180 and also a 400 down here. And if I looked at the 500, I'd find the exact same thing. 10 to the 6th divided by 180 and now multiplied by 500, like that. Okay, so if I run these numbers out real quick, what I end up finding, I find about 11. Oops, which one am I on here? About this one. I find about 11 here. I found 11. It doesn't look like I went ahead and did the other one for the 400. I did the 500. But not the 400. So it's probably 11-ish or possibly 12. I don't actually know the answer to that. And I don't seem to have my calculator with me. All right. All right, so I'm going to see, I would expect 11 fringes. Now, I told you before that it's generally less than 5. Okay, so this is, first of all, this is 180 lines per millimeter. Well, that's actually not too many. Then we just had, what do we have? We had 5,000 per centimeter. Yeah, all right, well, that's not too many. With a small wavelength, you're going to get narrower angles. I would definitely say you're not going to see much past 3 in this case, right? They dim out so quickly. Let's do one other thing with this, and then we'll call it good. Let's try and find out, because the patterns are such that I did kind of draw it here, but I didn't really take time to point it out. The pattern here is such that the angular spacing between these is increasing, right? So for the m equals 1, I have a certain angle difference between the two maxima. For the second one, I have a slightly larger angle difference between the two maxima. For the third one, I'm going to have a bigger distance between the maxima, okay? There is going to come a time when that angle difference gets large enough such that one of them overlaps with the previous maximum, or if you like, it overlaps with the next one, okay? So one question would be, all right, what fringe is overlapping when they get to that point? So let's see here. Let me do this. Right, so one way you could talk about that is to ask, when's the first angle at which the two maxima might be on top of each other, right? So, well, let's find the angle. Superimposed. Okay. At what angle are the two maxima superimposed? So the angle is, like I said, I should say, the angular difference is getting larger, right? So the angular difference is getting larger. Let's take a look at trying to find out what angles we're dealing with when we go to higher and higher maxima. All right. So if we do this, what we're going to do is say that when we go to looking at the sine of theta for each one of these, if I want these two maxima to be superimposed, well, then these sines are equal to each other, right? If I have two maxima which are right on top of each other, then the sines are exactly the same, right? So in this case, we're going to say that sine of theta 1 is equal to sine of theta 2. And what that means is the d's are going to be the same, but the m values will be different, okay? And they'll be different by the ratio of the wavelength. So you'll see here, I'm going to do m. Since it's lambda 1, I'm going to call this m1, lambda 1 over d, should equal m2 lambda 2 over d. Okay. So now the d's are going away with each other, and you can see that the M values are going to be proportional to the wavelength ratios, right? In other words, that M1 divided by M2 is the same as lambda 2 divided by lambda 1. And since lambda 2 divided by lambda 1 is 500 over 400, right? Yeah, 500 over 400. This is 5/4. That means that when M1 is 5, M2 is 4, and they lie right on top of each other. So where M1 is equal to 5, that's where M2 equal to 4 is located, is right on top of it. All right. Okay, so a little bit to work with on the diffraction gratings. The condition is not different than the double slit, but some of the usage is a little bit different than in the double slit. Okay, so I wanted to make you aware of that. And in terms of properties, what we're noticing is that, like I've said, the fringe widths are getting narrow. The fringes are getting very well defined, in other words. And in the meantime, between fringes, there's a whole lot of nothing. So that means as you increase the number of slits, those intermediate maxima are getting to be more numerous. As we saw with 3 slits, we had 1, 4 slits, we had 2, 5 slits, we had 3, in between the maxima, the principal maxima. So when you get to large numbers of slits, there's large numbers of intermediate maxima, but they are so dim, ultimately they are canceled out with all of the other. As you go to very large numbers of slits, they are ultimately all canceled out. All right. All right, so that's a little bit on the diffraction grating. Next time we'll talk a little bit about how to distinguish between, or should I say, what's the resolving power of a situation where you're trying to distinguish between 2 far away light sources. And we'll go on, do a little bit more with the diffraction grating, talk about its resolving power and its dispersion. And that's going to wrap up our section on wave optics. So by tomorrow, we will be pretty much done and over with waves. That should mean that we'll take the 1 week of study time, get ready for this first celebration, which is going to be on ray optics and wave optics, and we'll go hammer that one right out. So I bid you good day, folks, and I hope you enjoy a little bit of diffraction in the next few hours as it's still nice and fresh in your mind. And I will see you tomorrow. All righty, we'll pick it up there.